In 1913, Niels Bohr described the movement of electrons in the atom. In the Bohr model, electrons travel around the nucleus in circular orbits in much the same way that planets orbit the sun. This is a cross-sectional representation of the Bohr model. Because the orbits are three-dimensional, they are also called shells. The orbits are at fixed distances from the nucleus. As the radius of each orbit increases, the energy of the electrons in that orbit also increases. The existence of these Bohr orbits explains why atoms give off certain colors of light. Sodium has a yellow flame. In 1916, Sommerfeld showed that some orbits are elliptical in shape. This is a model that almost everyone is familiar with. Chemists use both the quantum mechanical and the Bohr models to understand and explain the properties of matter. Chemical changes and nuclear transformations can also be understood in terms of electrons, protons, and neutrons. The quark theory of modern physics goes further than that. In this theory, protons and neutrons are made of smaller particles called quarks. The electron is still a fundamental particle, hundreds of subatomic, one of three types of leptons. Hundreds of subatomic particles are also presumed to exist. We'll sum up our lesson after we return from this break. Hi, welcome to another episode of Chemistry in Action. For some time now, we've been talking about chemical reactions in terms of the various combinations that atoms and molecules make. This is a view from the outside. It does not tell us what molecules and atoms look like on the inside. Today, we will take our first detailed look at the inside of an atom. What does an atom look like? You would probably think of this image. You see it in cartoons, movies, magazines, and many other places. To understand how it came about, let's follow the development of the theories of atomic structure from the first attempts made in 400 BC to the models of the 20th century. The Bohr theory explained some observations, such as the spectrum of the hydrogen atom, but it could not explain the spectrum of other atoms. A new model, the quantum mechanical model, was more successful in this respect. The model was developed by Erwin Schrödinger and Max Born. Instead of treating the electron as a particle moving in orbits, Schrödinger described it in terms of a mathematical formula called a wave function. Born defined the wave function as a probability of finding the electron in a given volume outside the nucleus. Simplifying greatly, quantum theory describes a volume in space in which the probability of finding the electron is very high. The space in which the electron moves about is called the electron cloud. You might help your students understand this better by using this analogy. When an electric fan is at rest, you know exactly how many blades there are and where they are. When the blades start turning, you seem to see more than 3 blades. At full speed, all you see is a blur. You cannot say exactly where each blade is, but you know that there are 3 blades there. In the past half hour, we've traced how man's understanding of the ultimate structure of matter has developed through the centuries. From the simple and structured atoms proposed by the Greeks, we've gone through a series of models in which the structure of the atom becomes more and more complex. Thomson's plum pudding model, Rutherford's nuclear model, Bohr's atom with circular orbits, Sommerfeld's atom with elliptical orbits, and Schrödinger's and Born's electron cloud model. Scientists are still searching for the ultimate building blocks from which all things, stars, the earth, and the atom, are made. Are particles, such as electrons and quarks, truly fundamental, or do they, too, have parts? Who knows? Perhaps in the lifetime of Urian students, the answers will be found. Next time, our topic will be the distribution of electrons in the atom. Till then, this is your host, Ramon Miranda, wishing you a good day. Let us move on to 1911 and the alpha scattering experiment of Ernst Rutherford, one of Thomson's students. Rutherford on the right and Thomson on the left worked together at Cambridge University in England. Rutherford's setup included a source of high-energy alpha particles, a stationary metal foil, and a detector to track down the alpha particles. Using an alpha ray gun, he shot alpha particles at a very thin piece of gold foil and noted where the particles went. Rutherford's experiment is a really good example of how scientists use the scientific method. Here's something you can do in class to drive the point home. Invite your students to imagine what the gold foil looks like at the atomic level. We could start by imagining a very thin piece of metal foil, a few layers of atoms thick, perhaps. If we use billiard balls to represent atoms, we see that they are very closely packed hard spheres. The gold foil is mostly solid atoms with just a bit of empty space where the spheres don't touch. What happens if you shoot high-energy particles at this? Does the gold foil disintegrate upon impact of the alpha particles? Because of their high energy, most of the alpha particles went through the gold foil. But about 1 in 8,000 were deflected or scattered, usually at small angles or less often backwards. No one was probably more surprised at the results of this experiment than Rutherford himself. He wrote at that time, "It was about as credible as if you had fired a 16-inch shell at a piece of tissue paper and it came back and hit you." How would you interpret these results? Try to work that out while we pause for these messages. This is how we might imagine the electron cloud. For the hydrogen atom, the shape of the electron cloud is spherical. The single electron of hydrogen travels around the nucleus within this sphere. This sphere, or electron cloud, is also known as the atomic orbital of hydrogen. The atom, described this way, is deceptively simple. However, as we go on to other atoms, the atomic orbitals begin to look more complicated. The foil that we thought was solid does not seem so solid after all. What analogy could we think of to explain the results of Rutherford's experiment? Shooting the alpha particles at gold foil might be likened to firing bullets at an iron grill fence. Usually, the bullets pass through the fence undeflected. Occasionally, one hits an iron bar and ricochets. It might have been this kind of reasoning that led Rutherford to the conclusions of his experiment. He concluded that the atom is mostly empty space, composed of a small, heavy, positively charged nucleus, surrounded by tiny negatively charged masses, the electrons. Rutherford's model, also called the nuclear model of the atom, looks like this. If the nucleus were the size of a ping pong ball, the radius of the atom would be about 2 kilometers. This would explain why alpha particles go through 99.9% of the time. The positively charged alpha particles have a mass 4 times that of the hydrogen atom. On the other hand, electrons are relatively small and light and do not deflect the heavy, fast-moving alpha particles. When an alpha particle comes close to the nucleus, it is deflected from its straight line path because of the mutual repulsion of 2 positive charges. A direct hit on the nucleus would send the alpha particles back to its source. Rutherford's model raised many new questions. How are the electrons arranged around the nucleus? What is the nucleus made of? A number of years later, some of these questions began to be answered. Changes in the Rutherford model were made. Rutherford deduced in 1919 that a nucleus contained positively charged particles called protons. In 1932, his student James Chadwick established the existence of the neutron, another particle in the nucleus. The neutron has no electrical charge. The atomic number is the number of protons in the nucleus of an atom. It is also equivalent to the number of electrons in a neutral atom. The mass number is the total number of protons and neutrons in the nucleus of an atom. As more scientists began to delve more deeply into the nature of the atom, it became clear that the atom was composed of even smaller particles. It was no longer indivisible. The subatomic particles, electrons, protons, and neutrons, were discovered. Each time, a new model was formulated to make room for the newly discovered particle. In 1897, J.J. Thomson, through experiments with cathode ray tubes, showed that electrons were produced from all the electrodes he studied. He concluded that they were a fundamental constituent of matter. In 1904, Thomson proposed the plum pudding model of the atom. The Thomson atom is a uniform mass of positive charge in which electrons, or small negative charges, are scattered. Plum pudding is a dessert not familiar to all, so think of any pudding with raisins in it. The raisins dispersed in the pudding are the electrons, and the filling is a positively charged mass. In the 100 years between Dalton and Thomson, the idea of the atom changed from a simple structure without parts to a more complex one with parts. To start off a discussion on the structure of the atom, you could ask your students, what is matter made of? You might get all sorts of answers. Some will say that matter is composed of particles. Evidence for this? We detect the smell of flowers, or perfume, or vinegar. If we drop potassium permanganate crystals into a beaker of water, the color diffuses slowly throughout the water. Many people also have the idea that matter is made up of atoms and molecules. This is not a simple conclusion that just anyone makes from observing things. It requires a leap of the imagination. But that was the conclusion reached by the Greek philosophers Leucippus and Democritus in about 400 BC. They believed that one could take a specimen of matter and keep on subdividing it until it could no longer be further subdivided. That smallest piece of indivisible matter was called the atom. For Democritus, atoms of water were smooth. Atoms of fire had sharp edges. Your students might ask, why were these things thought by philosophers and not by scientists? We should realize that philosophers were the scientists of their times. They looked at the world around them and made rational explanations about what they saw. Philosophers were held in high esteem by their society. They worked with their minds, not with their hands. They did not see the need to check their deductions by doing actual experiments. By the 17th century, that had changed. Scientists now worked in laboratories to find answers to their questions. The notion that all matter was made up of atoms was now well accepted and taught by scientists of the day. In 1803, John Dalton revived the theories of Leucippus and Democritus. He proposed that atoms were the smallest particles of matter. Atoms of a specific substance were small, indivisible spheres of identical size. Dalton presumed that they had hooks on them so that they could combine to form other compounds. These are the symbols Dalton used to represent substances.